to be consistent.
Yeah, so it's my pleasure to introduce the first speaker of today, Daisuke Kishimoto from Kyoto University. And he will be talking about torsion in the space of commuting elements in a Lie group.
Thank you. Thank you for the introduction. This is based on joint work with my student, Masahiro Takeda. Okay, so let's first fix notation. Okay, throughout this talk, let G be a compact connected Lie group, and let T be its maximal torus, and let W denote the Weil group, its Weil group. And the object I'm going to talk about is the space HomZMG1, which is the connected component of the space of homomorphisms from Zm to G, containing the trivial element 1.1. And probably there are several talks explaining the background and some problems about this space, so I skipped that. And actually, I don't need to explain any background of this space because my problem is very naive. Okay, so let's start. Let me explain my problem. First, let's recall the Poincaré series of this space. Okay, let F be a field of characteristic not dividing the order of the Weil group W. Then there is a nice formula given by Baird on the cohomology of the space HomZMG1, and based on this formula, Ramras and Stiefel determined the Poincaré series of the space HomZMG1 over the field F. And remember that if the characteristic of F does not divide the order of the Weil group. Anyway, the Poincaré series is given like this. And the important point here is that the Poincaré series is independent from the field F as long as its characteristic does not divide the order of the Weil group. So this implies that HomZMG1 has no P torsion in homology if P does not divide the order of the Weil group. Because the mod B homology has the same Poincaré series as the rational homology, as if P does not divide the order of the Weil group. So let me ask this naive question. Naive problem. For each prime P, does the space HomZMG1 have P torsion in homology? Of course, there are some trivial cases that this space has P torsion in homology. For example, if G has P torsion in homology, then HomZMG1 has P torsion in homology because G is a retract of this space. And except for this kind of trivial cases, there are only two results on torsion in homology of this space. The first one is due to Baird, Jeffrey, and Selig, and also Crabbe, which states that for m greater than or equal to 2, HomZMSU2 has P torsion in homology if and only if P is 2. of course, the Weil group of SU2 is a cyclic group of order 2. So this proposition says that Hom ZMSU2 has all possible p-torsion in homology. And the second result is a very recent result by Adem, Gomez, and Grisset, which states that for m greater than or equal to 3, not 2, Hom ZM SPN1 has 2 torsion in homology. Of course, the Weil group of SPN has order 2 to the n times n factorial. So this says only a little information about torsion homology of this space. Right. And then, as I told you, these are the only results on torsion homology of Hom ZM G1. And here is my result. For m greater or equal to 2, Hom ZM SUN1 has p torsion in homology if and only if p is greater than n. So you know the Weil group of SUN is the symmetric group of in n-1 letters. Sorry, this is wrong. Sorry, this is n-1. The Weil group of SUN has order n-1 factorial. So this says that Hom ZM SUN1 has all possible p torsion in homology. Right. Okay, so any questions so far? Okay, so I'm going to tell the proof of this theorem, which includes many some interesting techniques, which are of independent interest. And this is the outline, very brief outline of the proof. First, we give a homotopy decomposition of Hom ZMG1 in terms of homotopy colimit of some functor Fn.
Excuse me, can I just briefly interrupt and ask, did you mean to say maybe p is smaller or equal to n or something?
Sorry, yeah.
You want all primes dividing n factorial, I guess.
Okay.
Sorry. So smaller than smaller or equal to n, I guess. Yeah.
Yeah.
Okay.
Sorry. Thank you.
Mm-hmm.
Thank you very much. So anyway, Hom ZM SUN has all possible p torsion in homology, so it has many torsions. Right. So
I'm sorry. Can I interrupt again? I am not. So what is the statement again? Sorry to. So p. So has p torsion in homology if and only if p is less or equal than n or n-1. But I believe if you take n equals 2, so I believe it should be less or equal than n, because if you take n equals 2, then
sorry, this is not what is SUN. And
right.
Sorry. Because the Weil group is sigma n. Sorry. Okay. Okay, so the first step is a homotopy decomposition. And I think this is one of the interesting technique, new technique. Okay, second, now we have a homotopy decomposition of our space by Hokorin. So we have a way to compute its homology, the Bausch field conspectral sequence, but it's really hard to compute the Bausch field conspectral sequence in general. So we need to reduce the problem. That's a functor FM hat. We will construct a functor FM hat such that its homology, the homology of Hokorim FM hat is a direct summand of the homology of Hokorim FM. So this is nothing but hom Zn G1. And the important point is that is the third step. The homology of Hokorim FM hat is much easier to compute than the homology of Hokorim FM. I mean, we will introduce a simplicial complex delta pk, which is defined in terms of the Weyl group of W, or Weyl group of G, such that the non-triviality of its mod P homology implies that the Hokorim of F2 hat has P torsion homology. So the problem is now reduced to compute the mod P homology of this simplicial complex and how to compute its homology. That's the fourth step. We compute its homology by using the extended Dynkin diagram of G. Okay. All right, so let me explain the first step. Oh, sorry. I have more results using our technique. The first one is that if G is simply connected, then Hom ZMG1 for M greater than or equal to 2 always has two torsion in homology. And the second result is this. For if G is simply connected, then we can determine the top homology of Hom ZMG1. And it's given like this. Okay. The top homology is Z mod 2 if M is even. The top homology of Hom ZMG1 is Z mod 2 if M is even, and Z if M is odd. So it depends on the parity. And the dimension of the top homology is given like this. And it's also depending on the parity of M. All right, so let's go into the homotopy decomposition. So we want to construct, we want to show that the space Hom ZMG1 is a Hokorim of some functor, and Hokorim, homotopy colimit is kind of a good fiber-wise space structure. So we need to find a good fiber-wise space structure on the space Hom ZMG1. And let's first fix the notation, the Stiefel diagram. Let phi be the set of roots of G. Then we can define the Stiefel diagram of G by the union like this, alpha inverse I, where alpha is a root and I is the integer, is an integer. For example, the Stiefel diagram of SP2 is given like this picture. And the white circle is the integer lattice. And we call each component of the complement of the Stiefel diagram the Weyl alcove. So this is one of the Weyl alcove of G. And the important point is that every Weyl alcove is bounded by walls determined by simple roots and the highest weight as the highest root. Okay. Okay, so let's consider another space, rep ZMG1. Okay, so hereafter, we are going to assume that G is simply connected and simple of rank n. If we assume G is simply connected, then the space rep ZG1 will be very simple. Okay. Anyway, here's the definition. Let rep ZMG1 denote the quotient of Hom ZMG1 by the conjugation action of G. So sometimes this is often called the character variety. And as I told you, if G is simply connected, rep ZG1 is very simple. It's a n simplex where n is the rank of G. The proof is this. By definition, rep ZG1 is the quotient of G by its conjugation action on itself. So it's isomorphic to the quotient of a maximal torus T by the action of Weil group. So it's nothing but the quotient of the Lie algebra of T by the affine Weil group. And it's nothing but the closure of the Weil alcove. And now the Weil alcove is an n simplex. So rep ZG1 is an n simplex. So, and the important point is that, again, I tell you again, this n simplex is bounded by faces determined by simple roots and highest roots. Everything is described in terms of these roots. Right, so now we define functor Fn. And as I said, we need to find a nice fiber-wise structure on the space Hom ZMG1. And the structure is actually given by this map pi, which is the composition of the projection onto Hom ZG1, and then the projection onto rep ZG1, which is an n simplex.
I'm sorry.
So,
I'm sorry to interrupt. Which projection are you taking? Are you projecting on the first coordinate or something like that?
First one. Yes.
Okay, thank you.
Of course, you can take M1, but it's a usual orthogonal projection. Right. So Hom ZMG1 is a fiber-wise space over an n simplex. And the base space is quite simple, and it's described in terms of roots of G. Now, let's consider its fiber, the fiber of pi. And now, and to understand its fiber, we use this simple lemma. We define the map phi from G mod T cross T to the M into Hom ZMG1 by this formula. Then this is surjected. This is quite simple. So this says that the fiber of pi is always a quotient of G mod T cross T to the M minus 1 fiber at any point. Of course, the fiber of pi changes if we change the point in an n simplex, the base n simplex. But if points x, y in delta n belong to the interior of the same face, then the fibers are the same. We can see this by using the fact that the fiber of pi is a quotient of G mod T cross T to the n minus 1. And okay, so the important point is this. Actually, the fiber pi inverse x is quite complicated, but at least we can describe it as a homotopy colimit of an explicit given functor. But it's really complicated, but we can control its top cell. This is the point of my talk. Right? Okay, so now we are considering a fiber-wise structure of Hom ZMG1 over an n simplex. And so then we define a functor Fm and use this fiber-wise structure to show that Hom ZMG1 is actually a Hokorimo of Fm. Okay. Now, okay, let's set notation. Let P of K denote the phase poset of a simplicial complex, K. And let sigma 0 denote the center of a simplex of delta n, as the center of a simplex sigma of delta n. Then we have this nice lemma. If sigma is a phase of tau, where sigma and tau are phases of delta n, then there is a map from pi inverse tau 0 into pi inverse sigma 0, having this functoriality. This means that the following proposition holds. Hom ZMG1 is obtained by gluing sigma times pi inverse sigma 0 by this map Q. This is nothing but saying that Hom ZMG1 is a Hokorimo of some functor. Right. And we get this theorem. Let's define a functor Fm from P of delta n into top by setting Fm sigma to be pi inverse sigma 0 and Fm tau to sigma to be Q sigma tau. Then Hom ZMG1 is a Hokorimo of Fm. Okay. Okay, now we get the homotopy decomposition. So let's move to the second step, which is a homology computation. Of course, we have already have a Hokorimo description of Hom ZMG1. We can compute its homology by this Bouts-Field conspectral sequence.
I just had a question.
Yeah.
So when you're saying it's the Hokolim, I mean, is it really the case that it's the colimit of this functor, and then the colimit and the homotopy colimit are homotopy equivalent, or
no, not
okay.
necessarily they are homotopy equivalent.
Okay, so you're really saying it's the homotopy.
Okay.
It is the homotopy
Actually,
colimit, maybe not the colimit.
No, actually, there is a criterion for. Actually, there is a natural map from Hokorimi onto Kolim, and there is a criterion by Ziegler and Zvarevich on for this projection being a homotopy equivalence. And actually we are considering a functor of a nice poset. So the condition should be the functor sends every morphism to a cofibration.
Right.
But our map Q sigma tau is not a cofibration.
Okay. Okay.
Okay, now, thank you. Now we have this Gauss field gun spectral sequence. This is a kind of cell spectral sequence with singular fibers. Right. So now let Qm be the dimension of G plus n times n minus 2. Then we know the dimension of Fm sigma. It's always Qm. It's independent from sigma. This is one of the consequences that we can control the top cell of this space. So our Gauss field gun spectral sequence has top line in dimension Qm. Right? So our spectral sequence is like this. Right, next, but there are many non-trivial elements in this shaded part, so it's almost hopeless to compute this spectral sequence. So we need to reduce the computation. That's the third step. The functor Fm. Okay, for phase sigma of delta n, let W sigma denote the subgroup of W generated by reflections defining sigma. As I told you, every sigma is bounded by simple roots and highest roots. So it's all of its faces are determined by some roots. So we can define W sigma. Now we define a functor Fm hat like this. Its value is always SQM. It's independent of the object, but it sends a morphism tau sigma to a map of degree W sigma mod W tau. Okay. So let's consider the Gauss field conspectual sequence of this for a Hokorimo Fm hat. The only non-trivial part is the zeroth line and QMth line. So this is much easier to compute than the Gauss field conspectual sequence for Hokorimo FM. And actually, we have this proposition. If M is even, then there is a natural transformation from FM into FM hat, which is an isomorphism in the top homology. And this is also one of the consequences that we can control the top cell of FM sigma. And the proof is like this. The top cell of FM sigma is controlled by using the action of W sigma on viral alcohols around the origin. And using this control, we can define a natural transformation from FM to FM hat by a pinch map onto the top cell. And the naturality of this pinch map can be described by the action of the viral group on the viral alcohols around the origin. And we get this natural transformation.
Excuse me, why do you need that M is even?
That actually, if M is odd, we can get a nice control on the top cell compared to the even cell. It's kind of the dependence on the parity of M on the top of the space home ZMG1. Is that okay?
A little confused, but maybe I'll ask you. read the
Okay.
paper.
Okay, let's talk about it later. All right, so now we can get this theorem. If M is even and the star is greater than or equal to Qm, then H star Hokolim F hat is a direct summand of H star Hokolim Fm. This is an easy, this is obtained by an easy comparison of the Bouts-Field conspectral sequence. If R is greater than or equal to, then the Bouts-Field conspectral sequence for Hokolim Fm looks like this, and Hokolim Fm hat looks like this. So there is no non-trivial differential in the Bouts-Field conspectral sequence for Hokolim Fm hat. And we have already seen that a natural transformation sends the top line isomorphically. Then we get this theorem. So if we can show that the homology of Hokolim Fm hat has p torsion in homology, then we can say that the homology, that the hom ZMG1 has p torsion in homology too. Okay. Right, so now this is the second step, and the third step is this, the complex delta pk. Okay, let delta pk be, we first define this complex. We define delta pk to be a subcomplex of delta n consisting of faces sigma such that p to the k plus 1 does not divide the order of w divided by the order of w sigma. This definition comes from the definition of Fm hat here. Then actually this complex computes the homology, some p torsion in homology of this top line. Okay, so if the order of w is p to the r times q, where p and q are prime, then there is a filtration starting from delta p0 ending and ends at delta pr, and where delta pr is the full n simplex. Right. So here's the theorem. If the mod p homology of delta pk is not trivial for some k, then Hokolim F2 hat has p torsion homology. This is because, as I told you, the homology of delta pk hat compute p torsion in the top line of the Bouts-Field conspectral sequence. And okay. Right. So now, the computation has been reduced to the computation of the mod p homology of this complex. But this complex, it's small, but it's hard to compute its homology directly. So we have to describe this complex in terms of some combinatorial features of G. So that's the extended Dynkin diagram. The extended Dynkin diagram of G is the Dynkin diagram of G added the highest root. So for example, the AN type n+1, sorry, Dynkin diagram is like this. Here's n points, and the highest root is added, and then also these AGs are added. So it's nothing but the cycle graph with n+1 vertices. So this is very good because it has high symmetry. Actually, this is the reason why we succeed to compute the homology of Hom-Zn SUN. Right. So now next we introduce a colored extended Dynkin diagram, which is the extended Dynkin diagram whose vertices are colored by black or white. Okay. So it's nothing but the two coloring of the extended Dynkin diagram. Right. So the important point is this lemma. There is a 1-to-1 correspondence between I faces of delta n and colored extended Dynkin diagrams with n-I black vertices. So if you want to count the number of faces of, sorry, this is not delta n. Oh, okay, this is good. So if you want to count the number of faces of delta pk, so you have to find the corresponding colored extended Dynkin diagrams. And actually, it's not so easy. It's easy, really. For example, if G is SUN plus 1, we can count all the number of faces of delta P0, and we can prove that its Euler characteristic is not 1. Still made a mistake. This is SUN.
I'm sorry, I have a little question. Sorry that I keep asking. Is there any way that you're gonna color the extended Dynkin diagram, or you're gonna look at all possible colorings?
Yeah, I have all possible coloring for faces of delta n, but if you restrict to the delta pk, not every colored Dynkin diagram corresponds to its face.
Okay.
But the definition of delta pk is quite simple too, so we can count the corresponding extended Dynkin diagram. Okay. Anyway, in this way, we can compute the Euler characteristic of delta p0 when G is SUN. Then now we can prove the main theorem. Now let P be a prime less than n. Since the Euler characteristic of delta p0 is not 1, this is a mod P Euler characteristic. Sorry. So it's not 1. So the mod P homology of delta P0 is not trivial. Because, okay. So this means that Hokolim F2 has P torsion in homology. So Hokolim F2 has P torsion in homology too. And now Hokolim F2 is nothing but Hom Z2 SUN. So we have seen that Home Z2 SUN1 has P torsion in homology. And now Home Z2G1 is a retroact of Home ZMG1. If M is greater than or equal to 2, then we have done. So far, then our technique or our proof works perfectly for SUN. But how about other cases? Unfortunately, it doesn't work well in some cases. For spin 2n, we can detect some P torsion in homology, like this theorem, in Home Zm spin 2n1. But unfortunately, we cannot detect all P torsion by our method. For example, if G is spin 10, then its Weyl group has order 2 to the 4 times 5 factorial. So delta 30, this is the only complex detecting 3 torsion in homology in our calculation. But we can see that delta 30 is contractible by using discrete Morse theory. So this doesn't work. But please remind that this doesn't imply that Home Zm spin 10.1 does not have 3 torsion in homology. This just says that my technique doesn't work. And actually, the case of spin 2n plus 1 and SPN, if we have the same problem, our complexes are contractible too. This is also seen by the discrete Morse theory. So what about the exceptional case? And when we are lucky, because except for 2 cases, our technique works. So except for E7 with P being 5 or 7, Home ZMG1 has P torsion in homology for all possible P when G is the exceptional Lie group. So what about this exceptional case, E7 with E5 or 7? In these cases, delta P0 is also the only complex detecting P torsion. And we have the same problem. This complex is contract, so it doesn't work. Okay. Right. But I think this failure. I think this failure comes from the fact that we are only considering the top cell of the space. So let me conjecture this. From ZMG1 for n greater than 1 has P torsion in homology if and only if P divides the order of W. So that means that it has all possible P torsion in homology. Okay, so that's all. Thank you.
Thank you very much for the nice talk. Are there any questions?
So I was just wondering, so you have this technique of pinching off the top cell. And I was just wondering, like, so you're collapsing everything below the top cell and then you get these splittings. Could you do something iteratively where, like, you collapse some lower skeleton and then Well, I mean, if you
Uh,
further collapse to the top cell, you get a splitting. So maybe the portion sort of in the middle there would also split off. I'm not quite sure, but I'm just wondering if there's some way to iterate the process to sort of get information further down.
yes, that's a very good question. Thank you. But I think actually the space FM sigma is quite complicated. It has many torsion in homology. So, and I have not succeeded to compute its homology actually. So such a kind of inductive step doesn't work because I don't have a good understanding its cell structure.
Okay.
So here is an idea. So what I think you did is, so you projected onto the first component and then went to the representation space. And then that was good because you knew what that was. It's is the wild alcove.
Mm-hmm.
But then the idea is, why don't you try to go once? I mean, what you're doing is, in any case, you are reducing everything to pairs, right? That's basically what you're doing, because you basically use the fact that for commuting pairs in homology, you get a direct summand. So that's basically what I understood. The idea is, why don't you, instead of projecting to the first component, you project to the first two components. In that case, you compare to the representation space with two components. But if G is simple and simply connected, that's known to be a weighted projected space. So you also have control over the base space. So maybe that's one way to improve in those other cases. I don't know. That's one idea that comes to mind.
Okay, thank you. But do you have any information about the rep Z SON? I think it's not so easy to understand.
Which one?
Rep Z SON.
SON. Oh,
it's
SON.
simple.
No. For SON is not simple.
Mm.
When the group is simply connected and simple, it is easy. But for SON, I don't think I know what that is. I mean, it's got many components.
Mm. Yes, that's right. Actually, this space is also deeply connected to the LS category of G. So I can't drop the assumption simply connected, and at the moment I have no idea to extend my technique. Thank you.
Can I just quickly ask, so these complexes that these delta P of K that detect the P torsion, I mean, to me, it looked like they were they were defined in such a way that they do the job. But have you seen those showing up anywhere else? I mean, are they somehow interesting, or do they have a description in terms of directly in terms of the group G itself? I mean, that's a subset of the conjugacy classes of G. Is there anything you can say about these complexes that sort of makes them even more interesting than just in that application?
Actually, no, because it's first, I have not seen it anywhere before, and it's actually quite complicated in general in the case of SUN or some other cases. So all I know is that it's a torsion space, and probably that's all I know, and it's quite complicated.
So you say the rational homology always vanishes of these
Yeah,
subcomplexes?
yeah. Actually, the homology of delta pk is kind of a part of the this top line,
Oh yeah, yeah.
and this top line is trivial in rational coefficient because its homology is computed by this using a different mixing the differential for the homology of delta n and this map. And also, if we work with the rational coefficient, this degree part, we can ignore this part, the degree part. It's actually isomorphic to the rational homology of the delta n, so it's trivial.
So I have a question. So what you're doing reminds me a lot of that stable splitting that was obtained by Adam and Cohen, which I've been thinking quite a lot how to compute the homology of the stable parts. So the question is, have you thought about the relationship between what you're doing, especially in the top cell and that splitting? It would be nice to know, like, for example, for SU2, where one knows everything.
Yes.
Is there any relationship?
Yeah, that's a very good question. I want to find it, and I'm trying, but it was not successful at the moment. Actually, I started considering this kind of Hokolim description because the stable splitting summands of them and Cohen are quite hard to understand. It's described only in the case of SU2. So to me, to find the p torsion in homology by using the stable stable splitting seems hopeless. So I started this fiber-wise, so a kind of dual things. But as I proceed this technique, I felt that there's some relation between this dual decomposition and then Cohen decomposition, but I'm not sure.
Okay, is there any other last question maybe? If this is not the case, then let's thank Daisuke again for a very nice talk.
Thank you.
And also thank
you so
you
much
for your commitment despite the late hour. Nice that you stayed up for us. And I guess wish you good night.
Yes, I will. I'm going to watch the video today, probably.
Right.
I'm going to bed.
Thank you so much. It was really nice.
Thank you. See you.
See you. Bye bye. And I guess we have a 6-minute break, and then we continue at the full hour. Or?
Simon, can I connect with two devices? I usually try to present with my iPad and then
I think
the audio
you can
on
connect
my
with
computer.
two.
Is that okay?
Yeah.
I'll try
Simon,
to
do you want to
then.
stop the recording?
Oh yes, I should stop the recording.